Hello folks, and welcome to our lesson on, or we're continuing our forces. We are going to talk about two objects and tension. So first off, I want to talk a little about something we've talked about in previous lessons. We want to talk about this idea of having two masses attached to a pulley, also known as Atwood's machine. Okay, so we got an M1, M2. Okay, and we want to make sure that we're really good at still drawing out our free body diagrams. Okay, we don't want to lose that skill. We want to make sure that we get better and better at doing these, and we want to include these in all word problems. And even just to understand what we're doing for a lot of problems, it's good to make sure we practice drawing in these free body diagrams. So when we're talking about two masses on a pulley, we're looking at something like this. And we know that we've got gravity pulling down on this one, so we have an FG1 attached to mass 1. We have an FG2 attached to mass 2. And then with these masses pulling down, we also have that tension force pulling up. Okay? And we remember from previous lessons that that tension is the same. Okay? It's equal and opposite. Okay? Another way we saw drawing this out is if we could actually draw, if we got rid of this pulley, it could help us understand that we have this M1 attached to M2 and something like that. And in which case, again, we have our tension pulling this one, we have the tension pulling this one. Okay, so let's mark that with a T. And then we have our FG2 pulling in that way, and we have our FG1 pulling in the opposite directions. Okay, so what we have here is both masses have an FG that is pulling them downwards, as we see here, and because they're connected by that rope, we see that they're in opposition to each other, right? We've got one force of gravity pulling one way, one force of gravity pulling the other way, right? That's in our linear situation. If we're looking at our pulley situation, well, if this mass is pulling this one down, it's pulling this mass up because of that rope. Or mass 2 is pulling down, it's pulling mass 1 up. Okay, so essentially these forces of gravity, although they're both pulling down, they are in opposition to each other. Okay, these forces are working in opposition to each other. Okay, and when it comes to understanding which way the masses will accelerate, remember this is the larger mass wins. Okay, we have the larger mass wins. And we want to understand that we've talked about this before. When we have two forces pulling in opposite directions, we've said that the larger force wins. Okay, well, in this case, it's the larger mass wins because that'll mean it'll have a larger force of gravity to cause that. Okay, and then since they are attached by the rope, the acceleration of these masses will be equal. Let's say mass 1 is a larger mass, it's going to accelerate downwards at one acceleration, and mass 2 is going to accelerate upwards with that same acceleration, okay, because that acceleration of the masses is equal. Okay. Other things I have on your notes here, the force of tension, which we've described as T here, exists all along the rope, right? That's tying in those lessons that we've dealt with in the past, okay? It acts equally along all points. Okay, it's an internal force acting in both directions at any point along the rope. So everywhere along this rope we have that same tension force. Okay, and then if we look over here, we realize that the tension cancels out of the F net because we have tension 1 going in that direction, we have tension 2 going this direction. They're just equal and opposite. So they cancel out of the F net equation. Okay. Some strategies for looking at these Atwood machine situations. When solving these problems, it is easiest to think, or it's easiest for us to choose the direction of the heavier mass winning as being positive. Okay, so if we just look at our heavier mass, let's assign that as positive. Because remember, we have our general conventions of what is positive and what is negative, right? So if we have this situation where we could either have our X and our Y axis, or we have our north, south, east, west. We usually think of positive and negative, positive and negative, right? But however, when we're looking at that pulley situation, where we've got these two different masses, in this situation, we get to still assign, like this is our general convention up here, where's our positives and negatives. However, when we're dealing with something like this, we might want to say that going down on this one is our positive direction, okay? So, or when we looked at our connection like this, well, this mass is going to win, so let's call this direction our positive, right? We can still change that around. It is arbitrary. This is our general convention. However, you can state it however you would like to. Okay, just make sure you do state that in your problems or in your drawing as such. Okay, remember that the acceleration of the two masses must be equal. Okay, so if you need to find out the separate accelerations, remember if you find out the net acceleration, that is the individual accelerations as well. Okay, and that last strategy, as I've drawn here, it could be easier to unfold that option into the linear situation as opposed to the vertical pulley free body diagram. Okay, let's take a look at our example on this, even though it's one that we've seen before. Two masses are suspended from a lightweight rope over a frictionless pulley as shown. So let's draw that one in. Okay, and so for M1, M2, I'm going to use 8 kilograms for mass 1 and 5 kilograms for mass 2. Okay, and we want to figure out what is the acceleration of these pieces. All right, well, let's continue. Since we've got this here, let's draw our free body diagram on here. We have our FG1, we have our FG2, okay, we have our tension going in both directions, and since we're frictionless, there is no friction to be dealt with. And we want to know what is the overall. Okay, now I've said sometimes it might be easier to unpack this drawing here into a different free body diagram, and if we did that, we have M1 connected to M2, okay, where I've kind of rotated this one on the side, so I have my tension force going in this direction. I have this tension force going in that direction. That would give me FG1 in this direction and FG2 in that direction. Okay. And I said in those strategies that we're going to assign the heavier mass winning as the positive direction. So based on the way I have this drawn here, that means that this is my positive direction, this is my negative, or when I've laid it out this way, this is my positive, and that is my negative. Okay, slightly different from what we've dealt with in the past, in fact, opposite from what we've dealt with in the past. However, the positive negatives, we assign those in directions. Okay, so we get to choose which is which. All right. To figure out their acceleration in this situation, we want to write out our F net formula. Right, because that F net equals our mass times acceleration, and we need to find out what this acceleration is. Okay, so what do we got for F net 1? Well, let's start with, we have this FG1, I'm going to assign that as a positive. And then I've got this tension going in the opposite direction, so it's minus tension. Then I've got this tension going in this direction, so that's another positive, okay, tension. And then I've got this FG going in the opposite direction, so now I can say minus FG2, okay? And then because our tension is equal and opposite, right, we've got this minus T plus T. this whole part cancels right out of the whole equation, as I've mentioned. So essentially what we're looking at then is this F net, or our M times A, is then just equal to our FG1 minus our FG2. And one thing I want to be clear on here, when we're talking about this F net, remember this is our total mass, right? We've got our M1 and M2 to figure out our FG1 and our FG2, but when we're looking at our F net, that is our total mass that we have to consider here. And so our acceleration is going to equal, this FG1 is our M1G minus our FG2, which is our M2G, and this is going to be divided by our total mass, which is our M1 plus our M2. Okay. Now I've done it where we've just manipulated the formula all the way along here, and then I can just plug in all my values. My 8 kilograms, my 9.81 meters per second squared, my 5 kilograms, 9.81 meters per second squared, my 8 and 5 kilograms. So I can enter that all in and calculate this all out. Or if you wanted, you could say at this step here, well, I can figure out my FG1 is my M1 times G, my FG2 is my M2 times G. Okay, that would give us 78.4 and 49 newtons respectively for those two. My total mass is M1 plus M2, which would be 13 kilograms. And that allows me to either plug those all into this formula or figure them out separate here. Either way, we get to a 2.26. Okay. However, we should kind of take a look back here and realize that we only had 2 sig figs for our mass. So our overall acceleration of this system is 2.3 meters per second squared. Okay. That'll be downwards on mass 1. That'd be upwards on mass 2 due to the fact that they are connected by this tension. Okay. And the note at the bottom of that is, remember, when we're calculating the acceleration, we need to use the total mass because F net is the acceleration of the entire system. And that entire system is all the masses involved in that system. Okay, hopefully that was mostly review for us. Okay, if not, it's good practice anyways. And let's move on to some more complex style problems. Okay, so we figured out the acceleration of the system. Let's figure out the tension in this rope. Okay, now we can't just figure out the tension based on this overall diagram that we have here because the two tension forces cancel each other out. And this is because that tension is an internal force. So in order for us to solve for tension, we have to look at just one mass only. Okay. And then for a strategy to solve this, it might be easier just to chop our diagram in half and consider only one of the masses. It doesn't matter which one we use because both tensions are equal. Okay, so I've left my diagram here and I've left my net acceleration down here. In fact, I'm going to add in that extra sig fig that we had from before, the 2.26 meters per second squared. Okay, and so let's take a look at this. Let's look at just M1 first. All right, well, if I did that, let's kind of, we're only looking at half of this, right? So for M1, we're going to look at this left-hand side, and then when we come back, we'll look at M2, we'll look at the right-hand side, and we'll show that both of these are equal. Okay, so our F net on mass 1, okay, this is going to equal, we've got force of gravity pulling down, and we have tension pulling it back up. Okay. And we also know this F net. Now, remember, we've split this in half. We're only looking at this one piece. Okay, so this F net here is different from the previous one. This one we are just looking at the M1 times A. Okay, and so if I rearrange my formula here, I get that tension is going to be equal to the FG, or I guess I could, yeah, FG1 minus M1A. Well, this is M1G minus M1A. Mass is 8 kilograms, gravity 9.81. Mass is 8 kilograms, acceleration is 2.26. Plug all of this in and we end up with 60.3 newtons. And when we apply sig figs, we would drop back down to 60 newtons. But I wanted to keep the extra sig fig in there because I want you to check this out when we look at mass 2. Okay, and please don't just take my word for it. Do these calculations. Make sure you are getting these values. Okay, but now looking at mass 2, we're looking at this right-hand side here. So we have our F net is equal to. Now for this one, we said we're accelerating. That's going to be our positive direction, right? So this one's accelerating upwards, right? Because we got to think of this as a whole system. Tensions, or this mass is pulling this one down, and this one's going up. Okay, so in that case, tension is our positive minus our FG2 pulling it down. Okay, and now we can then say that if, oh, and sorry, this is our F net for this one, since we're only looking at this block is M2 times A. And since we're looking for tension, I can manipulate this formula to say this is FG2 plus M2A. Okay, just brought that to the other side, and we have tension equals Fg2 times M2A. Once again, this Fg2 is our M2G. Okay, plugging in our values that we have, and again, I end up with 60.3 newtons. So a note here at the bottom, when finding the tension, we are only considering half of the equation. Therefore, we only use one mass when we're looking for the tension. Whereas when we're looking for the F net for the system, as we did in that previous example, we are looking at the total mass because we were looking at the total system. Whereas tension, we're only looking at one mass. Okay. Before we move on to two masses on an inclined plane, I want to look at a flat surface first and try to understand that. So we're going to look at two masses hanging off a table. Okay, so let's consider this example that we have here, where we have an 8 kilogram mass sitting on a frictionless table. Now I say frictionless, it's not included in the problem, but any problem that doesn't give us anything to talk about friction or any coefficient of friction, then we're going to make that assumption that we are dealing with frictionless or that our mu equals 0. Okay, so I have my 8 kilogram mass sitting on this frictionless table, attached along a rope to this 6 kilogram mass hanging off the edge. Let's start putting in some of our free body diagram vectors on here. All right. Well, we're going to have a gravity pulling this one down and a gravity pulling this one down. Obviously, that table's holding this up, so that means we're going to have a normal force pushing up, right? So I'm going to say this Fn on this one here. Okay. And because the force of gravity is not going to have effect on here, but it does here, I'm going to label this one my mass 1 and this one my mass 2. Okay, it is arbitrary. It's up to you on how you choose to do that. I just like to use the one that's going to be causing the motion to be my mass 1. Okay, which means that this is my Fg1 and this is my Fg2. And then because we're attached to this rope, that means that we also have our tension going upwards here, and then we have our tension causing this to move in that direction. Okay, so there is our free body diagram. As I said in the previous example there, we could also lay this out where we unpack this situation, like so, in which case, my free body diagram, I'm taking this and I'm swinging this up to the side. This is my FG1, this is my FG2. Since this one's sitting on the surface, I have that surface applying the normal force in that direction, and then I have my tension there and tension there. Okay? And our question for this one is to find the acceleration and the tension in the rope. Okay? Well, let's look at part A, our F net. Well, F net, because we are dealing with a coupled system, this is going to be our total mass times acceleration. And the only force that's causing this to move is going to be, well, I've got the FG1, which I'm going to assign the positive direction. I have the tension opposing that, so minus tension, plus I have the tension going in this direction. And once again, they cancel out. And so in essence here, we have our MTA is equal to, since we're talking force of gravity, our M1G. Or acceleration equals M1G divided by the total mass. So M1 is 6 kilograms times our 9.81 for G divided by our total mass, which is 8 plus 6, so 14. This gives me an acceleration of 4.2 meters per second squared. Okay. Now to figure out our tension, well, tension is the only thing causing this mass to accelerate. So when we're looking for tension, we're just going to look at this mass 2 in this example. And for this one, our F net, because we're looking at this piece here, the only force causing it to accelerate here is tension. So our tension equals F net. F net is M2 times A, the acceleration that we had over here. So our tension is this mass 2, or 8 kilograms, times our acceleration of 4.2 newtons, or sorry, 4.2 meters per second squared. We get 33.6 or 34 newtons for our tension. Okay, so that is a hanging mass and a horizontal mass. Hopefully we are good with those examples now. So we've dealt with 2 vertical pulleys, we've dealt with 2 masses attached to a pulley vertically. We have a horizontal and a vertical mass. Now let's move on to our inclined plane problems. We have 2 of these, one without friction and then one with friction. All right, here we are back with our next problem. Oh, I should put in my angle here, 30 degrees. So we have 2 masses on an inclined plane, okay? This mass is going to pull down vertically. This mass is going to pull down on an angle. So this poses a problem. Which direction will this accelerate? When we had our vertical pulleys, it was nice and easy. We just looked at the larger mass and that let us know which was which. However, in this situation, it's not quite that straightforward. Okay, so we've got to look at 2 different situations. We've got force of gravity pulling this one down. However, since gravity is pulling straight down, sorry, I'm just going to pull this out of here. Gravity is pulling straight down. we are actually just looking at, and this is frictionless, we are just looking at this port here, which is our FG parallel. So that's what we need to compare. So I'm going to call this mass 1 and this one mass 2, just so we can write these in. So I'm trying to compare then FG1 with FG2 parallel. Okay? So we need to look at both of these in order to figure out the acceleration to understand what's going on. Because if we look at this free body, I have tension going up here, I have tension going here, I have a normal force going this way, and that would be equal to my FG perpendicular over here. Okay? Like that. Okay? And I'll just write this up here. Our angle in this case is that 30 degrees. Okay, just because I ran out of space. All right, so we have our free body diagram drawn in here. This was FG2. Okay, so we've applied all of these. And in order to figure out our F net, we need to know which direction this is going to happen and which direction this is going to go. So let's compare those, because really it's this FG1 pulling straight down in comparison with this FG2 pulling parallel, that's pulling it down the ramp. Okay, so let's look at force 1 that could cause us to accelerate, which is this FG1. Okay, well, FG1 equals M1G. So 4 kilograms times our 9.81, 39.2 newtons. Okay, and that's going to be pulling it this way. Let's figure out what our FG2. So our force 2 that we need to consider that could accelerate this is our FG2 parallel. Okay, and FG2 parallel is equal to M2G sine theta. So we got our 6 kilogram mass times our 9.81 times the sine of 30. This gives me 29.4 newtons. Okay. This now we have the direction that this is going to travel. This force pulling down, 39.2, outweighs the force going in this direction of 29.4. So our entire system is going to accelerate in this direction. Okay, so that means when I go to solve my F net, this FG1 is going to win out. That is my positive direction. So I'm going to say FG1 minus tension plus tension, right? Because FG is going here. I've got tension going up. I've got tension going this way. So again, those cancel out. You can start to cancel those out of your overall problem, but I just wanted to show those in here for now. And then I'm going to subtract this force going in the opposite direction of the FG2 parallel. Okay. Now, since we're looking at the acceleration of the whole system, that means our F net here is the total mass times acceleration is going to equal FG1 minus FG2 parallel, right? Because these cancel out. So acceleration is going to equal my FG1, my 39.2 newtons, minus my FG2 parallel, my 29.4 newtons, and I'm going to divide this out by my total mass, which is 4 plus 6, so 10 kilograms. This gives me an overall acceleration of the system of 0.98 meters per second squared. Okay, hopefully that helps out. That was part A, was finding the acceleration of the masses. Part B is trying to find the tension in the rope. Okay, so let's get rid of this here. And this free body looks more complicated, although it's really not that much more complicated because there's no friction, so we're not worried about this portion yet. But when I go to figure out my tension, I'm going to look at this mass 1, okay? Because what we're looking here then is just at this mass, our F net equals our Fg1 minus tension. Or we can manipulate this formula and say that tension is equal to my Fg1 minus my F net. Fg1, we had previously calculated that as this 39.2 newtons. And I'm going to subtract from that my F net. And now remember, just like in that last one, we're only looking at this piece here, right? We're looking at tension, we're only looking at one mass. So that means my F net is just my M1 times my previously found acceleration of 0.98. So 39.2 minus 4 times 0.98 gives me a tension force of 35 newtons. Okay, so once again, when we're looking at the acceleration of the entire system, we're looking at this total mass. However, when we're looking at the tension, we're looking at just one piece. So my F net is just that single mass. Okay, hopefully that helps with these frictionless inclined planes. Let's move on to our most complicated problem that we're going to deal with, and that is two masses in a similar setup, but with a frictioned surface. Okay, so here's our setup for our final problem. We have a 24 kilogram mass here and a 28 kilogram mass on this inclined plane. The angle of our plane is 40 degrees and the coefficient of friction on this ramp is 0.15. Now, we have to figure out which direction this is going to travel, right? So let's start looking at just some of our free body diagram. We have Fg1. Here is our Fg2. Now, we can break down, because we're on this inclined plane, this is going to be our Fg parallel. And we have an Fg perpendicular here. We have our normal force in this direction. We have tension along the rope here. Okay, so far this is very similar to the previous free body diagram that we had. However, now we have to consider this force of friction. And as we all remember, force of friction opposes the motion. We're only talking friction on this ramp, okay, not associated with pulley. So we have no friction on this mass. Our coefficient of friction was for this mass 2 on this inclined plane. And in order to draw in where this force of friction is, we first need to find out what the motion is, because if this block is going to win and go down the ramp, then friction is going to go this direction. However, if this mass wins and that pulls this mass up the ramp, that means friction is going in that direction. So just like we did as the first step in that first problem, or in the last problem there, we need to look at which force is going to win. So force 1, I'm looking at this one here, which is my Fg1. Then I'm going to look at my second force, my force 2, which is going to be this Fg parallel. Okay. So for this first one, we've got our M1G, which is 24 times 9.8, so 235.2 newtons. And then looking at this FG parallel, this is my M2G sine of theta. So plugging in my 28, my 9.81, and my 40 degrees, I end up with a value of 176.4 newtons. So FG1 wins. That means it's going to go down. That's going to pull this up here. So opposing the motion of this block going up the ramp means that I have my force of friction going in that opposite direction. Okay. Before I write out my F net, I know that I'm going to need to have that force of friction involved in this situation. Okay, force of friction, as we remember, is mu times Fn. My Fn in this case means my Fg perpendicular. So my force of friction is then mu times my M2G cosine of theta. Right? If Fg parallel is mg sine theta, Fg perpendicular is mg cosine theta. So here is my formula for the force of friction. I plug in my 0.15, my 28 kilograms, 9.81, and the cosine of 40 degrees. I end up with a force of friction equal to 31.5 newtons. Okay? Just want to simplify and make some space here. So this was my FG1 was 235, FG parallel was this 176.4, and my force of friction is equal to 31.5. Okay, these are all forces, these are all in newtons. Now we can look at the acceleration of the system by looking at our F net. All right. As I said in the previous ones, we're going to start off with the force that's winning, in this case Fg1. That is our positive. I would subtract my tension and add my tension, but as I said, we can start to eliminate those. So I'm going to cancel out those tensions before I write them into my formula. They're already canceled. So Fg1 minus my force is going in this direction. So my Fg parallel, and also subtracting my force of friction. F net here, right? This is my total mass times acceleration, and that's going to equal 235.2 newtons minus 176.4 minus 31.5. So acceleration is going to equal to all of this divided by my total mass, the 24 plus the 28. This gives me a net acceleration of 0.525. So, actually I'll do a different color over here for you. Acceleration equals 0.53 meters per second squared. Okay. If at any point you go through and you do this and you have a negative force, okay, so obviously we know which one's going to win here between these two, okay, or looking at in this direction, but if the combined forces in the opposite direction, the Fg parallel and the force of friction, if those combine to be greater than this force, we just end up with a stationary object. We don't actually have acceleration. I don't think I'll be mean enough to give you any of those in a test type situation, but just to be aware for future. Okay. Now, that was part A. Part B here, we want to find the tension in this rope. Okay. Well, I think to solve for tension in this one, this looks pretty complicated. Okay. Even if not all that complicated, but even still we would have tension, friction, and parallel. So I'm going to look at just this mass 1 to figure out my tension. And I know then that my F net is going to equal my FG1 minus my tension. Okay, well, F net is M1 times A. Oh, actually, sorry, before I do that, I should re-manipulate my formula here and say that tension is going to equal FG1 minus F net. Okay, so FG1 we have up here 235.2 newtons. My F net, because we're just looking again at one piece here, this is going to be minus M1A, or my 24 kilograms times my acceleration of 0.525. So we take our 28. This F net here is only 14.7, so I end up with a tension force of 220.5 newtons. Based on our overall problem only having 2 sig figs, our tension force is 220 newtons. Okay. Hopefully we have a better understanding of how to use pulleys and inclined planes and how they can help us to lift heavy objects. And have a good understanding of how these inclined planes work with pulleys as well and these multiple objects. Okay, if you have any questions, please post those on the website and I'll get back to those as soon as possible. Be safe, stay healthy.